Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera. Good morning. This lecture we will cover the relative motion analysis. In particular, we will now go from velocity to acceleration. So we have done this before for the velocity, where for the general plane motion we have the translation motion and also the rotational motion. And usually, in order to view these components, we use relative motion. And in relative motion, we have the relative coordinate system, which is similar to the translating reference we have done for the particles. So here is the case where I show you the two links OA and AB, and OA is rotating about a fixed axis rotation about O, and B is rotating about A, and then from there, let's say the velocity of OA is omega OA, and the angular velocity of AB is omega AB. So for us to determine what is the velocity of B, so we can use from the position vector. This is OA, which is position vector A, or we write it as RA. And then we have position vector from A to B, which is position vector relative position vector B relative to A. And then finally we have this OB line, which is position vector B relative to O, and O is not moving, so we can just write position vector B. And from there we write the position vector equation. Position vector B equals to position vector A plus position vector B relative to A. This is the set of equation, and you can use the same way of notation, and we can write velocity of B equals to velocity of A plus velocity of B relative to A. And again, you can use the same approach to get the acceleration of B equals to the acceleration of A plus the acceleration of B relative to A. So if you can draw the vector equation, position vector equation, it will also lead you to the velocity and finally the acceleration vector equation. So it's better for us to understand this by looking at one example, and this is some basics which I would like us to go through together. So for example, in this simple system, we have a link OA, and that link is rotating about a fixed axis rotation O. So let's see, this is the fixed axis rotation O, and this is fixed, so I'm gonna do this fixed. And then so this OA is rotating about fixed axis rotation, and it has a angular velocity of omega and angular acceleration of alpha, and we know the position vector is OA, and we want to find the tangential component of the acceleration and the normal component of the acceleration. This is our y-axis system. So in this case, because of our right hand system, omega is given to us is 2k radian per second, and we can find the position vector of OA. So position vector of OA is position vector of A is 2i, and position and omega of OA, so is 2k radian per second, and alpha is given as 5k radian per second. So we want to find the tangential and the normal component of the acceleration. So here is AT equals to alpha cross R. So we can now substitute the value. Alpha, we know what alpha is. Alpha is 5k. And then what is R? R is 2i. So we have the answer k cross I is 10j. So the answer is tangential velocity is 10j meter per second square. And then we can find the normal acceleration. It is equals to omega cross omega cross omega cross R. And we can simplify this with minus omega square R. This will help us not to carry out the vector operation. So we can use the simplified version, this minus omega square R. So let's see. What is omega? It's minus omega is 2 square, and what is our R? R is 2i. Yeah, so minus 4 times 2 is minus 8, so it's minus 8i. So we can now write the acceleration of A equals to AA in the normal direction plus AA in the tangential direction. I should have write A here. Okay, so that's equals to, in the normal direction is minus 8i, and in the tangential direction is 10j. Yeah, so after that we can put the units there. 8i plus 10j meter per second square. So that's our answer for the acceleration of A. It's a straightforward application of the system. Yeah. So now let's try a more complicated example. So in here you have a link OA and you have a link AB. Yeah. And OA is rotating counterclockwise with an angular speed of 4 radian per second and angular acceleration of 5 radian per second square. AB is rotating clockwise, omega AB is 2 radian per second, and alpha AB is 10 radian per second. And we have chosen our coordinate system to be this yx. So we have to determine the acceleration of point B. So the first thing to do is find the position vector of each component. So we know what RA is, position vector of A, it is 2 meter to the right. So we can now write that 2 meter to the right is 2i. What about RB? What about RB? RB position vector of B is 2 meter to the right and 0.5 meter to the top. So we can write RB equals to 2i plus 0.5 g. And then finally, what is the position vector of B relative to A? B to A is 0.5 meter going up. Yeah, B is 0.5 meter up of A, so we can write there 0.5 g. This is key. If you cannot write the vector, then we cannot solve it. The other things that we need to do is to find the vector for each of the angular velocity and angular acceleration. Because we are using y-axis system, so our positive x, y, z is to be out of this plane of the screen. So currently the counterclockwise are the positive one. So we can say that, or we can write now, omega OA is 4k radian per second. I don't have to write the unit, just say some space here. Alpha OA is 5k radian per second square. What about omega AB? It is in the negative. So it's negative 2k radian per second, and alpha AB, it is negative 10 radian per second square. So space here, I will write the units there. So each block we have these important sets of equations. Let me put this. So we got position vector B relative to A. We got omega OA, alpha OA, omega AB, and alpha AB. Okay, so it's a k here, 10k radian per second square. So we have now with us the equation for the vector, and we can write the equation for the acceleration. And down here we have written here for alpha A is alpha A. So here we have acceleration of A is alpha OA cross vector A minus omega square position vector A relative to O is should be a vector. And for this is for A, and for B relative to A, we got alpha AB cross position vector B relative to A minus omega square B position vector B relative to A. So we can now substitute the values in order to help us to find the solution. Let me clear this. So alpha OA, we know alpha OA is 5K. We know RA is 2I. Yeah. Then we have minus omega square. OA is 4. Position vector A is 2I. So 2I. Okay. Then we can start with this one. Alpha AB. Alpha AB is minus 10K. Minus 10K. And position vector B relative to A is 0.5J. Minus omega AB. Omega AB is 2. So 2 square. And position vector B relative to A is 0.5J. So K cross I, we can now find K cross I is J. So 5 by 2 is 10. So it's 10J. Minus 16. This is 16 times 2, 32I. Minus 32I. Plus 10K, K cross J is minus I, minus positive. So 5, K cross J is 5I. And then 2 square is 4. 4 times 0.5 is 2. So it's 2J minus 2J. So acceleration of A is summation of all this. So 10J minus 2J is 8J. Yeah, minus 32 plus 5 is 27, minus 27I. So it's minus 27I plus 8J. So that is the answer for position. Right, I have to write the units here. So the units is in meter per second square. So that's the sample, a relatively simple example of the acceleration of point B. Let's try another example which may be a little bit more challenging. So here is a case. So we will continue with this example 2, as we have seen this figure before. So in this example 2, the caller C is moving downward with acceleration of 1 meter per second square and velocity of 2 meter per second, and which gives the link CB and AB angular velocity. For CB is 10 radian per second counterclockwise, and omega AB also 10 radian per second counterclockwise. And distance between AB vertically is 0.2 meter, and the horizontal separation between C and B is 0.2 meter. And the question is determine the angular acceleration of CB and AB at this instance. They want to find, or we want to find alpha AB and alpha CB. So let me write it down here. So we want to find alpha CB and alpha AB. So how do we approach this problem? So there's similar techniques that have been used before, which is to draw the coordinate system, and then we find the position vector, determine each position vector, and we write the acceleration vector equation as before, and calculate for each component. So Let's try to do that now. So the first thing is to draw the coordinate system. So we typically use our XY system as shown here, XY, and we find the position vector of interest. So I can now draw the position vector. This is position vector C, and this is position vector B, and this is position vector C relative to B. So I wrote that position vector B. Yeah. So and then we determine each position vector. So I can now write position vector C, for example, which is it's of no interest, but I just write down it's 0.2 meter to the left, so it's minus 0.2 I. Position vector B is 0.2 meter down below, so B is minus 0.2 J. And position vector C relative to B, position vector C relative to B is C is 0.2 meters to the left and 0.2 meters to the top of B. So it's minus 0.2 I plus 0.2 J. So that's the position vector. So then I can write the acceleration vector equation. So I can write that from here. I know that position vector C equals to position vector B plus position vector C relative to B, and from there I can write the acceleration vector C equals to acceleration vector B plus acceleration vector C relative to B. What are the data that we have? The data that we have is that we know that AB has got two components, so we can write that alpha AB cross position vector B minus omega square AB position vector B. And then we have got the C relative to B. Acceleration of C relative to B is alpha BC cross position vector C relative to B minus omega CB, omega BC square, position vector C relative to B. So that's this is all vectors. And last one, do I know about what do we know about AC? AC is given is 2 meter per second, 1 meter per second square downwards, so minus 1 G. So we have got all the necessary components for us to do the calculation. So let me box this. Yeah. So we've got these position vectors, all of the position vectors, and we have got all the equations that we need. Yeah. So what about this omega? Omega AB, I've got to write it somewhere here. Omega AB, oops. Omega AB is 10K, is counterclockwise, so using our right hand system is a 10K system. So 10K, and omega x that is equals to omega BC also is 10K. So you might have some problem of finding why this. So you should use the right hand system to determine the values. So now we can do the calculation for each component. So let's do for the B component. So B equals to alpha AB cross B minus B. So alpha AB, we just assume that alpha AB is K. So alpha AB K, that's our assumption. cross position vector B is minus 0.2G. Minus omega square is 10, 10 square, and then is minus 0.2G. Yeah, so that is our solution. So we will have K cross J, so is minus I, so minus and minus is positive, this is minus, so minus 0.2 alpha AB I. Minus 100, minus, that's positive, so it's positive 0.100, so plus 20J. Okay, so that's the assertion of B. What about assertion of BC? So assertion of C relative to B, similar formula. We said alpha BCK cross position vector C relative to B is minus 0.2I plus 0.2J. Yeah, and then minus omega 10 square. Position vector is again omega square minus omega square minus 0.2I plus 0.2J. So K cross I is J, so minus 0.2 alpha BCJ. K cross J is minus I, so plus 0.2 alpha BCI. Okay. Minus 100 times 20, so that's equals to plus 20I plus 20G. Yeah, minus 0.2I 100 minus, this is minus, so minus 20G. So we now can arrange all this equation in terms of, and we know that AC is minus 1 meter per second square. So we know that AC is given here 1 meter per second square. So we can write down this whole equation. So AC is minus 1J equals to AB 0.2 alpha ABI plus 20J plus minus 0.2 alpha BCJ plus 0.2 alpha BCI plus 20I minus 20J. Yeah, so we'll solve the I component first. So 0 equals to 0.2 alpha AB, okay, plus 0.2 alpha BC plus 20. Am I right? 100 minus, yeah, 20I minus 20J, yep. So we have 0.2 alpha AB plus 0.2 alpha BC equals to 20, sorry, minus 20 equals minus 20. So that's our first equation. And then we can solve for the J part. Minus 1 equals to 20 minus 0.2 alpha BC okay, minus 20. So we can have 20 minus 20, so alpha BC equals to 5 radian per second square. Okay, so when you know alpha BC is radian per second square, you can substitute the value here and you will then get your alpha AB to be 95 minus 95 radian per second square. So that's the answer to the questions that you are looking for. Okay, so I'll stop there, and I hope you can follow the examples that proven here, so that you can. These are relatively simple geometry. We will move into more examples later on in the next lecture. Okay, thank you, and please follow the lecture and put your effort into understanding this problem. It will benefit you in later. Thank you.